someone that I talked to has at some point watched his lectures in Islam on YouTube, which taught me what I know about localization and Islam. So it's a real pleasure to have you here. I'll teach you about more from the robotics side of things. I hope you will learn something new.
Awesome. Thank you very much for the introduction. So I want to tell you a little bit about the robotics activities that we have been doing, but I actually want to focus mainly on where I think the future, where I foresee my future. So which problems we will be tackling over the next, let's say, 7 years in the lab, and I want to show you a little bit of direction in which we want to go. So I'm working in robotics since approximately 2001, when I started my master's thesis in Boston Motors Lab in Frankfurt, where I also studied. I'm working on a large number of different autonomous systems, from logistic platforms with KUKA, autonomous driving, flying UAVs, urban terrain navigation, underground navigation. In 2014, I got appointed to the University of Bonn as a professor of photogrammetry, so I'm now doing kind of photogrammetry, robotics in combination. And I want to share with you a little bit the activities we have been doing over the last years, now one of the projects, European projects, and then see where we are heading to and where else semantic starts to play a larger role. So if you go back to kind of robotics, what are the two key things you need to do in robotics? There are two main problems that we have. The first one is you have a state estimate problem. So you want to know what is the state of the world. That can be the location of your platform in the environment. That can be what the environment looks like. That's kind of the first question you need to answer. So turning your perceptions into kind of your problem. And the second thing is which action should I actually execute. So what should I do based on where I am? And so far, one of the typical techniques in order to approach the state estimation problem is a recursive-based filter. Typically, you're running an online session, so you don't want to collect all the data beforehand and then create the best possible model. We're often interested in doing online state estimation. And a recursive-based filter is, let's say, a standard technique to do that. In terms of action selection, you often use something which is related to the Bellman equation, which tells you basically what is the reward, or some reward function, and what should the robot do to maximize its expected future reward. So a lot of those problems boil down to those two equations. It's not really true, but it's a simplification of that. So in the end, we have state estimation problems running on our platform. And basically, say we do some actions in order to kind of reach our goal or get can use learning techniques, which perform some of the state estimation problems, or even turn the state estimation problem directly into actions. So maybe that may not be the most accurate description in the learning age, but if we actually go to the standard models, that's kind of the key robotics on one slide. That's probably how I would describe that. And I want to start with a project that I've been working on, explaining a little bit of the state estimation and action selection problem for that. And starting with the Rovina project, which is a European project on cultural heritage preservation, that I've been coordinating from 2013 to 2016. All those projects are run with, 6 to 8 partners, building systems which do hopefully useful things. And the first one, looking into how can we map hazardous environments with mobile robots in full autonomy mode, looking into catacombs under Roman Naples at our application scenarios. And then since 2014-15, I've been looking into agriculture and agricultural applications in robotics, which I think are very challenging environments where robotics can be a big game changer, and perception is very important, collecting data in order to do a service for our society. And it's one of the big challenges I think that we have or will be facing. And that will bring me to the future, which I can basically be seen as an extension for that. So in Germany we have this So who of you has been in a Roman catacomb or in an Italian catacomb? So very small number. That's a very large underground environment. Basically consists of tunnels built around 2,000 years back. They have been used for burying people. They've been used for assemblies. Very young Christian roots go back to that. And they are hazardous environments. So there's an image of a catacomb. You can see here part of the catacomb being collapsed. That's a challenge or a hazard, but it's probably not that critical because they don't collapse that often as long as we don't have construction sites. But the problem is they're actually filled with radon gas, radioactive gas, which is collected in those catacombs, basically based on the stones, which, if you breathe it, it goes into interaction with the water you have in your lung and which stay in your lungs. And therefore, in those catacombs, you're only allowed to go in there for around 15 minutes. Then you need to leave, and the deeper you go, the higher the radon concentrations. So it's one of the things where archaeologists can only spend a small amount of time in those catacombs and do their reconstruction work and their preservation work, and then you actually have to leave. That's one of the challenges. So the maps of those catacombs that we have basically look like this. These are old hand-drawn maps, and generated at the point in time where people were not caring about radon or knowing about radon concentration. And so this is the best thing that we have right now. The other problem that you have, they are all owned by the Vatican, and they are very, very critical in letting people in there. And I think we got access to some of those catacombs that for the last 40 people, no one was allowed to take any measurements inside. Basically because we only were computer scientists and engineers, and not having historians in there, which use this data in order to make any interpretation of what's going on, which turned out to be very simple in the beginning, but turned out to have several legal fights with the Vatican up to now on what happens with that data and how people had tried to sneak into those catacombs and record data they were not supposed to record. That was another endeavor which I hadn't foreseen in the beginning. So if you go to one of those catacombs, this video footage that you get. That was me running around with a video camera. There's actually a lot of lighting in the Priscilla catacomb. What you can see, so these are walls. All those walls are actually all burying places, so people are buried in there. They are around, let's say, 1 meter wide, 180 high, something like this. They go for several kilometers. In underground under Rome, under Naples, a lot of Italian cities. Partially they're collapsed. You find a lot of bones and skulls in there, so you collect a huge amount in there. There are several floors, so this catacomb has actually 6 floors. If you go there to visit, you're only allowed to enter the first layer, first level, because of the radon concentration. And they're actually very interesting cultural sites. Sometimes you come into really open spaces with a lot of paintings, and actually very, very beautiful sites with a lot of cultural. So in this catacomb, for example, 2 popes are actually buried in there. So how we do the exploration? So we build a platform, which looks like this. It's a Mesa element platform, so one of small bases. The rest is all custom made. And we try to build a system which is as cheap as possible so that actually archaeologists in the end has a chance for using this platform. So what you see in front are 3 externally connect-like cameras, which have the advantage of providing depth information very easily to us with not a lot of computational resources. Over here is actually an arc consisting of 7 cameras in order to do 3 reconstructions and 50-watt LED lights. The issue here is that it's a very narrow and confined space, so a standard stereo setup would have 2 calls to the obstacles, so it took us a while to actually engineer this arc to actually get the 3 reconstructions. The laptops are stored in here. There's basically a small sarcophage because those catacombs are very dirty. 100% humidity, so you have a lot of challenges with your hardware there. We also have 3D laser, which in the end we didn't use. So we thought it would be more useful in the beginning, but in the end we actually haven't used it in most of the setups. It's a quite nice platform, pretty rough. So this is can climb stairs. So this is one of the first experiments that we did when I was moving to Bonn. So you can go with those platforms up and down the staircases. As long as the staircase is not completely round, you actually can climb them very nicely. We put a lot of efforts to design this platform having a low center of gravity, a low center of mass, so that the platform doesn't flip even if it tries to climb staircases. That was actually a kind of challenge to design this platform, navigate with this platform. At the end, it was a pretty useful device for exploring these environments in here, and it's quite agile in terms of its navigation. So in the end, what are the key challenges that we need to address if you want to build those systems exploring those sites? So we need localization and mapping. On the one side, we need that online in order to make navigation decisions, but we also want to collect data to later maybe offload that to a cluster and compute a really precise reconstruction. We need to have traversability analysis. We need to know where we can go. We need to select appropriate target locations, so path planning, path execution of things that we need for online processing. And this should be resource friendly. We only have 2 notebooks, no GPU. It should be fast, 0 human interaction. If possible, it should be cheap because archaeologists should be using this platform. This was causing a couple of design constraints that we had in there, and it took a few iterations until we had the platform in a way that we actually use it. So the first question you need to answer, where can we actually navigate? So you see that platform, you can go inside, it goes back, it has to revert back, so you cannot turn most of those places. These are more open areas in here. It's pretty dark, you need to bring your own light source, which also causes some challenges for the 3D reconstructions. And at least for the traversability information, we basically use the Kinect cameras or Xeons sitting in front, building these types of map here. We say green is traversable, red is not traversable, light hasn't been seen. We can actually do local planning on those data. And so these are the images that you actually generate in those catacombs and the depth image. And you basically run a classification system, not very sophisticated, on those models. And so in this case, the scale is actually too high for the platform to climb up. So you can see here, these are those bars corresponding to the staircase. Sorry, I can't navigate there. This all had to run online, so in the end, So 2013, 2014, 20 frames per second on the base on one CPU. That was great, but already one CPU, one part of the CPU was gone. Everything had to run on that platform. On one single notebook computer, because the second one was there only for logging the cameras, these semi-resolution cameras. The other platform was busy. Then we can look at local modes. We need to decide where to go, where to get our next observations from. It's basically exploration, very similar to what Daniel Kramer has explained here before with the UAVs. So we want to reduce the uncertainty of the environment. We actually need to take into account where we can navigate. We want to avoid turns, because the turns with those tracked platforms are really bad because of odometry and state estimation problems. And that took us a while. Local exploration works quite fine, but the global exploration is actually challenged for those large environments where we need actually multiple missions. So we start developing a system where we say, okay, we have those hand-drawn maps. Let's exploit those hand-drawn maps and try to align them with what we see. And we then built a kind of what I call a near-optimal exploration strategy where we can do rough planning, these of the global structure on those maps using an offline TSP approach, and then deploy the platform there, which makes sure everything in those small areas is observed and we get actually near-optimal exploration trajectories. And it also allows us to plan multiple missions. So there's an example of 2 exploration missions, one shown in blue, one shown in red over here, on how we explore those catacombs and select the data of those environments. Being efficient is important, and the good thing is, if you do this, we have some background information. You can use it. We have a near-optimal exploration strategy, and then only have to build that locally. At least you have an idea what your platform is doing, which actually turns out to be quite helpful. But of course, we can also do that without then reverting basically to a frontier exploration. This is the closest area which you haven't seen in order to reduce uncertainty about what the environment looks like. So this is kind of one of the platforms at that time, another camera arc when we developed it. So you can see it's driving around. We were able to drive basically follow this corridor, exploring the entrance of the catacomb in Priscilla. So with models, so we can do the 3D reconstruction with the Kinect basically with an optimized version of ICP that actually works quite well. You can also see there are narrow spaces. One of the questions: how accurate does your model need to be? 45 centimeters is needed, otherwise you cannot see the platform for those environments. The structural motion system, which was running offline using this camera, was work done by Luc van Gogh, who was also in this project. In the beginning, a lot of challenges because we are bringing our own light sources. The light source is moving the platform, which like this feature-based approach can be actually very tricky. So in the end, we maybe develop a variant of the surf descriptor for being able or more robust to carry out light sources and recording this data. In the end, this was an offline processing platform for obtaining this 3D reconstruction. So these were the first reconstructions that we actually generated. We're also able, given that we are seeing the surface from different viewpoints, to classify the material, what's going on there. See some of those blue areas over here, these are areas which have been obstructed from the field of view because the camera was rather on that platform. We also had to do multiple iterations with that platform, a lot of tests. We spent in the catacombs in Rome, but luckily we filmed also old World War II bunkers near Bonn. Those over here, which are actually very similar to those catacombs, we could test our platform without shipping it to Rome, which always was an effort. Also, we need techniques in order to avoid the mapping fails. We don't want to lose our platform in there. So we have systems that the system can recover its and go back to its homing location, even if the map is corrupt, and trying to optimize this. And here you can see the camera arc. A lot of light we needed to get those scenes, driving through the environment, and doing those reconstructions. There was also the time where a friend of mine, Christian Plagemann, who was sharing the office with me in Freiburg, he went to Google, and one of the guys was doing the Google Cardboard. So one of the first having the prototype of the Google Cardboard available, and then actually used the 3D models that we built in order to build 3D models of those catacombs as part of the Priscilla catacomb. We can, with this Google Cardboard, although the visualization is, I think, done from an Oculus Rift, because of the high quality, I can look around. It's done even now with more cameras, so that we get a 3D reconstruction of the map before in an appropriate way. And if you go there and there, you see one of those small chapels that are built inside those catacombs, where you can see that they actually have a lot of paintings in there, and actually trying to do reconstruction of those paintings. They started from Italy, trying to commercialize this. So if you're in the catacomb in Priscilla, you can actually buy that from other catacombs, so that you try to attract visitors, also see other catacombs. You can just put it over a phone, put the cardboard on, and then get those 3D reconstruction into those sites. So it's kind of an interesting platform, and it turned out that with the technology that we have, we can actually build those platforms even for a price which is, let's say, in the order of 30,000 euros in the end, which is not too much compared to what Oculus is using in equipment right now. They will use a terrestrial laser scanner easily ranging from 30 to 100,000 euro for getting 3D reconstructions. We still need humans bringing the laser scanner into the environment, and this is something which you can do without. So right now there are people from the United Nations International Council of Monuments and Sites in Italy, which are using part of the technology that we developed in order to do 3D reconstructions. We can go quite far with those local sensors. Precision doesn't matter that much. Robustness is more important. All the precision stuff can actually be done offline for actually getting the final reconstructions. And there was relatively little semantics needed. In the beginning, we started, so Bastian and Luc van Gogh were two people, a project person here looking into semantics as well. For the cooperation of the platform, that was not that much needed at that point in time. Although you can do things like estimating what materials you are using there, this is all nice stuff, but this is stuff which doesn't need to be run on the robot, doesn't need to run online, and the robot is, let's say, to a very degree exploiting that. As it's a little bit about semantics here today, I think now we'll move forward and look into agricultural robotics. So things, environments which look like this, completely different to the underground environments, because they're semantic, there's more. And I think robots are a very interesting technology to change the landscape of agriculture as we see today. And so why is this the case? Why is this important? You can do very little calculation in an envelope, saying what is the local population, what estimate of the world population that we have. And if you look to the amount of biomass which is typically produced from crops that we need between 2010 and 2050, within 40 years, this is approximately the same amount of biomass that we've produced from the beginning of mankind to 2010. So over a much larger period of time. And the key thing is we need to do this now in a sustainable manner. Sustainable means in the sense that the way we are doing this, we are not compromising our future generations to reduce the biomass that they need. And this is a big challenge. So within 40 years, we have to grow a lot of biomass. It's getting better after 2050. So if you look, what are the key milestones? Having the key milestones in crop production. So 10,000 years ago, people were using hand tools to maintain the fields in a better way. Around 1900, roughly, tractors came up, which were a big game changer in how we produce our fields. 2050, agrochemicals kicked in, herbicides, breeding became more important. I mean, breeding was done before, but breeding at a much larger scale. Generating crops with certain properties, like putting more energy into the corn rather than the size of the plant itself. And today, precision agriculture, let's say, machines which know, or working semi-autonomously, I would say, having a good idea of where they are is a changer, or changes agriculture today. And I foresee that full digitalization and autonomy will be the next game changer. So let me tell you what are the problems that we have today and how we can actually address them, where I think robotics can play an important role. So today what we're using a massive amount of agrochemicals. So this is the use of agrochemicals over time. Although I have to say that China is one of the key players in using agrochemicals, but also in Europe we use we can simply increase the area of the fields that we are producing. It's which causes a lot of challenges, and also climate change doesn't simplify our life. You can argue that on a local perspective, we may even be better in Europe with a lot of climate change because we can grow crops differently. People are debating about that, but globally this is a big challenge. So in the end, what we must look into is the question is how can we reduce the negative impact of crop production on ecosystems, and at the same point in time address the demand for an increased yield. These are kind of two opposing things. And so what are ways for reducing impact and for increasing yields? If you look to increasing yield, is something which is known for a couple of years, so it's not very novel. Basically, two things you can do. Breeding and crop management are the two main factors. We have to distinguish here between something which is called the potential yield and the actual yield. So the potential yield is what you can produce in the field if everything's perfect. There are no weeds, there are no plant diseases, that's kind of what we have as the potential yield. But the reality is different, so the actual yield is lower than the potential yield. And so we increase both of them in order to get out more. So how can we do this? At the same point in time, we need to reduce our inputs, which are fertilizers and other agrochemicals. And also breeding and management are two ways for doing this, especially the management part. Robotics can play an important role here, and I will show you a few examples. But also in the context of breeding, robotics can play an important role, not for the breeding activities itself, but for monitoring how genetically modified plants or the result of your breeding experiments performs in the field, because you need to make large experiments. And robotic technology can help it. So my claim is that robotics and large-scale visualization will be a game changer for agriculture. That's what I believe. I believe that we will have autonomous systems on our field. The question is, will this be huge autonomous tractors, or more autonomous than they are right now, or will this be a large number of small machines working in parallel? Very open, I don't know. Probably we'll start with big machines and then going towards small machines, because there's certain advantages like soil compaction is dramatically reduced. There are a lot of advantages in this. And also, exploiting large-scale data, learning, doing intelligent decisions is something which is important, because understanding crop growth, they're good models for that, but there's still a lot of things that we can do in order to make predictions. You know, to do simulations saying, if we change crop management in a certain way, which impact will this have on yield? Which impact will this have on our ecosystem? Is something which is a very challenging question. And the other thing is, if you do an experiment, it's hard. Do the experiments once per year. So if we do our sugar beet experiment, something I'm working with, we have basically planted in spring. So we have 6 acres we need to do all our experiments, and then we need to wait for a year. Sugar beets, okay, you can plant them multiple times during the year, but other crops is more challenging. So doing experiments and simulations is harder compared to the standard indoor robotic stuff that we are doing. And I want to now look into one very concrete example. How can we reduce the amount of agrochemicals for more sustainable crop production using robotics? I want to show you a few examples of what we can do right now, where and what I think we can do for the next years, and how this may look like maybe 7, 8, 10 years down the line. So I will want to look into weeds especially, firstly. So one of the agrochemicals that I use to kind of kill the weeds, only maintain the plants that you want to have, which probably are the chemicals which have been killing a lot of weeds, which starts to be a serious issue, declining the biodiversity through herbicides. There are two ways to do weed control. One is conventional spraying, so you go with the tractor over the field, you spray your field with herbicide uniformly. It's kind of a standard approach. Maybe you vary it from field to field, depending how much weeds you have. Or you do it in an organic farming way, and this is done in a manual way. Either a lot of people lying behind a tractor, picking out the weeds and maintaining the crops, or actually sitting on the field, going over the field. It's clear this is chemical-free, it's great, but it doesn't scale. It comes at a substantial amount of cost, and also labor starts to be a lot of time. People doing this. It's probably not the job that you would invent your children to do, or wish your children to do. But this starts to be a serious issue. And I think that robotics and robotics technology can be a game changer here, because it can drive over the field. If you understand what we see, we can actually treat every plant in a specific way. So plant-specific treatment at large scale is one of the things that we can do with perception and action in closed loop. And for that, semantic matters. So we need to understand what we are seeing. So what you see here in this example, this is an RGB image that we take inside this platform. This is the first version of an agricultural robot that we're using. And what we want to have is basically something like this. Saying, okay, this is a sugar beet plant, this is a sugar beet plant, and these are weeds. So what is a system which can tell me that, so we then can act and kind of care about those and kill those guys. So on a very high level, there are kind of 2 steps which are needed for that. First, we need to have a plant classification system, which, given input image, turns this into these labels here. The second thing, it has something which kind of kills those weeds over here, so that only the crop that we want to have actually maintains. This is the first step, the plant classification system. How to do that? Very similar to what we have seen before, semantic segmentation is one of the approaches that we want to do in here. And today you're probably doing this with a CNN-based pipeline. For doing this, I'm not a deep learning expert. We are using it in the labs, but I'm probably not the person who tells you how to design the best network in order to achieve this task. But what I can do here, make a small advertisement for something that Andres Villosa, one of my PhD students, has been developing over the last years, which is called Bonnet, which is a system called deep learning for robotics. It's not that it pushes the boundaries of deep learning for us, essentially, but it makes it trivial to use for non-experts. And that's something that we as roboticists care about. We don't necessarily care about how do we get those semantics. I mean, sometimes we do, sometimes we not do. But we want to do something useful with it.